Thank you. Good afternoon. Today I'll talk about halo-independent bounds on the non-relativistic effective theory of WIMP-nucleon scattering. This talk is based on our recent paper, which is in collaboration with Stefanos Kopel and Sang-Yun Kang. As we know, cold dark matter is believed to provide 25% of the energy density of our universe. However, detected only through so far through gravitational effects. The WIMPs are one of the most popular candidates for cold dark matter. So a popular technique that is used to search for WIMPs or WIMP signal is direct detection, whose physics is mainly based on scattering of WIMPs against nuclear targets. Now, the same WIMP nuclear scattering can trigger capture of WIMPs in celestial bodies such as Sun, where this captured particle can annihilate themselves to produce neutrino signals. Neutrino telescopes, which are looking for this kind of neutrino signal, can also constrain the WIMP scenario. Now, the estimated WIMP signal for both direct detection and capture depends on the velocity distribution of WIMPs in our local neighborhood. Non-detection of any new signal in direct detection or neutrino telescope puts upper limit on the WIMP nucleus interaction. Now, while predicting or estimating the signal and comparing with the experimental data, two classes of major uncertainties arise. One for the nature of WIMP nucleus interaction, and another one for the WIMP speed distribution in the solar frame that determines the incoming WIMP flux. So for WIMP nucleus interaction, the most common choice has been either standard spin independent or standard spin dependent interactions. While for WIMP speed distribution, the most common choice has been Maxwell-Boltzmann speed distribution in the galactic frame and then boosted to the solar frame, which is called standard halo model. Note that here U is the WIMP speed with respect to solar frame. Now, this Maxwell-Boltzmann distribution, which is based on some simple isothermal model, provides only a zeroth order approximation to the WIMP speed distribution. Numerical simulation of galaxy formation can only tell us about the statistical average properties of the WIMP speed distribution. Various recent merger events can add sizable non-thermal components to the WIMP speed distribution. Also, growing number of observed dwarf galaxies suggests that our halo may not be perfectly thermalized. So due to these reasons, one needs some halo-independent approach where the main strategy is to find the most conservative bounds on the interaction from the null searches of the detector with only constraints that the local WIMP speed distribution is normalized to 1, where this speed distribution or WIMP speed distribution can have any profile. Now, direct detection experiments are sensitive only for a WIMP speed that is larger than some threshold speed. Now, this threshold speed is corresponding to the recoil energy threshold of the detector. So, direct detection cannot probe or cover the full WIMP speed range. Velocity distribution, which is concentrated below this threshold speed, the direct detection rate will be 0. So, one cannot use only direct detection to probe to have this for this halo-independent approach. On the other hand, capture of WIMPs in Sun is favored for low WIMP speed. Incoming WIMP particle, after being scattered against the nucleus in the Sun, will be captured if its velocity after scattering is less than the local escape velocity. Otherwise, it's difficult to capture. Hence, for the low WIMP speeds are more favored for capture. After being captured, this WIMP particle continues to scatter against the nuclear targets in the Sun and settle inside the core, where they can annihilate to produce various standard model particles and ultimately neutrino signal, which can be observed in neutrino telescopes. Since direct detection are more favored for high WIMP speeds and capture or neutrino signal is more favored for low WIMP speed, so one possible solution to the halo-independent approach is to combine these two. However, inclusion of capture brings two additional assumptions. One is the assumption on equilibrium between capture and annihilation in the Sun, and another one is the assumption on the WIMP annihilation channel. This complementarity between direct detection and capture was used by Ferrer et al. To develop a straightforward method that gives conservative constraints on the WIMP interactions independent of the WIMP speed distribution. This is called halo-independent bounds. However, this halo-independent method was applied to the case of standard spin-independent or standard spin-dependent interactions without assuming any general structure for the WIMP nucleus interaction. Non-observation of any new physics predicted by popular extension of standard model, for example, SUSY, motivates one for a bottom-up approach that goes beyond the standard spin-independent or standard spin-dependent scenario. We know that usually the WIMP nucleus scattering process is non-relativistic, both in direct detection and in the case of capture in the sun. So based on this, in general, WIMP nucleon interaction can be parameterized in terms of non-relativistic effective Hamiltonian that complies with the Galilean symmetry. And this effective Hamiltonian look like this, where these OIs are the Galilean invariant operators, and this Ci tau as the Wilson coefficients, with tau is the isospin. And coupling with proton and neutron can be obtained from these Wilson coefficients in this way. Non-relativistic Galilean invariant operators for a WIMP of spin half are total 14s in number. They are expressed up to linear terms in the WIMP's velocity. Operator O1 is the standard spin-independent operator. Operator O4 is standard spin-dependent operator. These operators are the most general building blocks of low-energy scattering theory. The discussion of halo-independent method when WIMP nucleus interaction is driven by each of these operators is crucial for understanding the more general scenario involving several non-relativistic operators at the same time. Now, using the effective Hamiltonian, one can obtain the differential cross-section for WIMP nucleus scattering, which can be used to calculate the number of expected events in a direct detection experiments in this way, where epsilon is the efficiency of the detector, nt is the number of target per unit mass of the detector, m is the total mass of the detector, and tau is the time exposure, and rho is the local dark matter density, and fu is the WIMP speed distribution. Using the same differential cross section, one can obtain the capture rate of WIMPs in the sun in this way, where eta t is the number of various nuclear targets inside the sun. So in sun, the incoming WIMP speed is strongly enhanced due to the large gravitational pull of the sun, which is encoded here in the local escape velocity, which increase the incoming WIMP speed. And also there is a maximum WIMP speed up to which capture is kinematically possible. We assume equilibrium between WIMP capture and annihilation in the sun, which implies the capture rate of one WIMP is equal to the annihilation rate of two WIMPs. So this assumption is a valid assumption according to the present experimental sensitivity and given the fact that WIMP is the total dark matter. In this case, neutrino flux from WIMP annihilation in the sun is solely determined by the capture rate. In order to estimate the halo-independent bound, one can first estimate the single stream upper limit on the coupling, which is basically the upper limit when all WIMPs are concentrated in a single stream. So this plot shows the single stream upper limit as a function of WIMP stream speed. So for a O1 operator, which is standard spin independent operator, WIMP proton coupling, and with this mass. So limit from neutrino telescope, which is based on capture signal, is more favored for low WIMP speed, and limits for direct detection are more favored for high WIMP speed. Taking a convolution between these two types of limit, the maximum value of this convolution is, let's say, C star, then one can show that the halo-independent upper limit on the coupling square is like this, twice C star square, where the factor of 2 is due to the fact that we combine two different types of experiments from two different WIMP speed range. We obtain halo-independent bound for each pairs of the neutrino telescope and direct detection experiments, and the most constraining limit is taken as a final halo-independent bound. So these are the example of halo-independent bound on different coupling. So these black lines indicate the halo-independent bound on a coupling that implies any point above this black line is disallowed by experimental data independent of the wind speed distribution. For comparison, we also show the limits from neutrino telescope and limits from direct detection separately, which are obtained assuming standard halo model. So these are other operators. So these plots are our main results. So in order to understand some general features from this plot, we estimate the degree of relaxation of halo-independent bound compared to that obtained for standard halo model. For this, we define a relaxing factor, which is basically the ratio between the halo-independent bound and the strongest upper limit obtained for standard halo model. So this is an example of relaxing factor as a function of WIMP mass for WIMP-nucleon coupling. As you can see, for all of these operators shows some general feature, that is a moderate relaxing factor in low and high WIMP mass regime and large relaxing factor in the intermediate mass regime. Note that small relaxing factor implies that Maxwell-Boltzmann distribution is not a very optimistic assumption. The relaxing factor for WIMP-proton coupling is somewhat more interesting. Here we saw some departure from the general pattern, which are obtained for mainly for spin-dependent operators. In fact, smallest relaxing factor obtained for operator O4, which is standard spin-dependent operator, and operator O7, which is spin-dependent and velocity-dependent operator. Then followed by other spin-dependent operators, which are comparatively higher momentum suppression. So with this, I'd like to summarize that combining direct detection and neutrino search results, we obtain halo-independent bounds on each of the coupling of non-relativistic Hamiltonian that drives the scattering of WIMP against nuclei. We consider one single coupling at a time, which is a first step towards more general scenario involving several non-relativistic operators. For most of the couplings, we found that the degree of relaxation of halo-independent bounds compared to standard halo model is moderate for low and high WIMP mass regime, and more moderate values of bound relaxation is obtained for standard spin-dependent type WIMP-proton couplings. So all this implies that standard halo model may not be a very optimistic choice. In other case, experimental sensitivity should depend on the WIMP speed distribution. With this, I'd like to thank you all for your attention.
So any question?
So this result from neutrino telescopes, that will depend upon the branching of dark matter annihilation into neutrinos.
Yes.
Now, that's an independent assumption, or are you getting it from these 14 operators itself?
No, that is an independent assumption.
So
so inclusion of this neutrino signal brings an additional assumption, which is the
branching into neutrinos would
yes,
be something
yes.
else.
And we consider BB bar, which gives kind of more conservative bounds.
Okay, so from BB bar you get the neutrino from the decay.
Yes, yes.
Okay, thank you.
Okay, if there is no more question, let's thank the speaker.